Can start now.
Let's get started. Okay, so this lecture is going to cover three different topics, three pretty distinct different topics: access control, error handling, and cycles. So the goal is to give you a sense of tracks. Started with these three different areas. So I'm Jorgen. That's my Twitter handle. I'm the founder of Saga Tarot, and I've been building on internet computers since 2021. Without further ado, if you want to follow along, there are code examples that you can follow. I'll actually paste this if I can. 1 second, I'll paste this link into chat in case anybody wants to follow along. There we go. Okay, so starting with access control, which is for those super special times when you don't want to let any person do anything on your software. So basically, adding an access control layer to our contracts is going to let us say only this specific person or these types of people can perform these certain actions within our system. And the really simple use case that we'll focus on for now is admin only type things on our NFT contracts. Things like allowing somebody to configure metadata or to manage assets or to call our minting functions, things of that nature. So we're going to look at a couple different ways that we could add access control, starting with a really simple paradigm. As we're probably all familiar by this point in the boot camp, when you create a canister, the message to create that canister is comes to the IC with a caller, which we can capture and make that into store that in a stable variable in our contract and say this is the administrator of our function. And then we can perform an assertion using the assert method that's built into Motoko to make sure that anybody who's or somebody who's calling a sensitive function is the admin before allowing them to proceed. So this is a really basic example of what that looks like. We have an actor definition where we have the shared keyword at the front, which allows us to actually, quick question for chat. Can you guys see my mouse on my screen right now? So can I use it to point at things?
Yes, we
can. Okay, good. Yeah, so we're unpacking the message parameter that gets sent along with shared function calls, shared actor calls. Going to unpack that to capture the caller parameter out of it. And then we're going to actually cast that into the creator variable so that wherever we reference this variable in our contract body, it's going to be under a name that's kind of explicit about what it is. Because in some of our other functions, like this function down here called mySecret, where we're going to perform an assertion, if we were to say we forgot to put this caller chunk in here in our function definition, we would actually be using the caller definition from one step up in the scope, which might have been the creator of the contract. So if we forget to put this chunk in here, then our assertion would actually just be checking to see if the person who created the contract is the owner, and we would have some bad false negatives there. So anyways, we capture this creator variable and we stuff that into some stable state. And then on a function which we expose publicly, mySecret, which holds on to grandma's secret lasagna recipe, we want to make sure that only authorized people can get the output of this method, And so we assert that the person calling this function is the owner, and now we have very simple access control in place. So if you're following along, you can punch in these DFX commands, just deploy and try to call the function with the principal which created the canister. You'll see a success. And then if you switch, you will then see a failure. So this is what that output would look like. Using the main identity, you would get grandma's secret lasagna recipe, and using an alternate identity, you would get a message that looks like this. Replica returned an error. This canister trapped explicitly because an assertion failed, and it's telling us the file and the exact line where the assertion failed. So that's really easy. That's super simple, and that could be all that you want for your use case. But what if we wanted the ability to maintain a group of admins who are allowed to do certain things? This is going to be really similar, because we're going to use basically the same method. Oh, actually, I'm getting ahead of myself. Sorry. This is if we wanted to allow our admin to change who the admin is, we can simply assign a new owner inside of a set owner function like this. So I'm going to glance over that pretty quickly, because I think it's probably fairly clear to the Motoko Bootcampers at this stage in the game. So getting to what I was saying before, what if we want to have multiple administrators? Sometimes it's nice to be able to allow, our friends, coworkers to be able to do a couple of things on the contract as well. So let's jump over to, I'm going to jump over to my code editor here, and we'll take a look at what this contract looks like. So the same basic setup. We're going to capture the creator, and we're going to store it in stable state. But this time we're going to initialize our admins as a list of principals, with the first value being our creator. And then we'll add on this function here called isAdmin, which is going to take a principal, and it's going to return a Boolean value for whether or not that principal is one of our administrators. So all we need to do to perform that check is to find inside of our array of admins any value which matches the principal that's given. And if we find one, then yes, this person is an admin. And if we do not, then no, that person is not an administrator. Now, in our super secret method where we're storing the lasagna recipe, we can call an assertion using isAdmin caller. And we can add on to this contract, if we'd like, a couple of utility methods down here that will allow us to just manipulate the state of our admins. So we can, this could actually be a query method here, list out all of the admins that we have in our system. And we can provide a method to remove particular admins from our system. And we can add another method to add more admins to our system as well. For both of the state altering methods, we're going to want to make sure that we only let admins call those two. And I won't go into the details of implementing these functions now. If you do want to check them out, then you can grab the link in chat. Or I guess if you're watching this video after the live recording, then there'll be a link for you to click on as well to get to the main repo. Great. Okay, so if we wanted to test this out, here are some commands that we could run. What we're going to do in this first line here is capture the identity of an alternate principal. Then we'll swap back over to the main identity in the DFX command line, and we'll deploy the example. And then we can call the add admins function, which accepts a list of principals, and we'll just pass in the principal of our alternate identity. And then if we swap to that alternate identity and call the secret recipe, the expected output there would be that we do in fact get the recipe because we are now an admin. So that's going to sort of wrap up pretty quickly the basics of access control that we're going to cover. With these patterns, you'll be able to cover a number of different use cases. There's obviously much more to access control. Just picture a world where you have different groups of people who need different categories of permissions. Sometimes in software, this might be called different permissions systems. And you may want to allow one group of people to call these 3 methods and have another group of people or one specific person, call another 2 methods. And by adding on some more complicated data structures and applying somewhat of the same principles here of just performing a security assertion, you can achieve an access control layer. So you can grab the source code and try this out in your own contracts. And a quick water break, and then we're going to jump into error handling. Okay, so error handling, as I was actually discussing with Seb before we started, can seem like maybe when you're writing your code, not such an important thing to do. But as soon as you run into a problem with somebody else's code, or with code that you wrote, a couple weeks ago, a couple days ago, it's critical to be able to tell exactly what went wrong. And how we handle and report our errors is critical to that. So the official Motoko documentation is really good on error handling. So a lot of what's in this portion of the lecture is actually going to mirror that pretty closely. So I'm just going to paste into the chat the official error documentation. Oops, I don't know what I just pasted into chat, but don't think it's what I meant to paste. There's the right one. All right, so when we're looking at the simple admin system, we used the assert to throw an error, if you will. The assert keyword, or the assert method, when given a conditional or an expression that evaluates to a false value, it will trap the contract. So it's really quick to write, but it's pretty useless in the error message that it provides back to us. So if we look at the error message that we get back from an assertion again, we can see the line, the file and the line where the assertion occurred, which that's very nice actually in cases where you have access to the source, but quite often you don't have access to the source. So you'll end up looking at a file and a line, but that doesn't mean anything to you. So you do not know what went wrong with the input that you provided to cause this situation and what you can do on your end to fix it. It's a pretty arcane output to receive back. So a note on trapping a contract. So when a contract traps, it means it's entered an unrecoverable state, and the entire request that was passed to the canister will be thrown out, and none of the state changes that have occurred within the call will be committed to the canister's state. There are exceptions to that we won't get into in too much detail now, but using or asynchronicity and using await can change the behavior of what state is or isn't committed. So that's something to keep an eye on. In fact, async and await is probably the one of the biggest things to keep your eye on in terms of pitfalls when writing on the IC, but that's for another time. So the good news is that Motoko provides two modules that are much better for error handling. We have results and we have error. We also have the option primitive, which is good for certain use cases. And these are the three different methods that the official Motoko documentation recommends for dealing with errors. So we'll start with option values because they're kind of the simplest. One of the perks of Motoko, and Rust does this as well, is anytime you have an option value, so a value which could either contain something or it could be a null value, Motoko is going to force you to deal with that null case. And you might think, well, why is that a perk? That sounds like an annoying thing to have to deal with. And perhaps sometimes the syntax for unpacking those values in Motoko isn't always the most fun. But the perk is that by forcing you to deal with the null case, it removes a category of bug which would otherwise be able to occur in your program, where a case where a value does not exist and your program expects it to exist. So that's actually really nice. Now we'll get to what I think is the primary limitation of option values, which is that when you receive a null value back from a method that you're calling, pretend you're calling a method on a canister that you don't own, and it gives you a null value back. It doesn't really tell you anything. It says you got nothing. So that's great in situations where you don't need additional information. For example, we used array.find in one of the code examples above. And if we receive a null value back from array.find, it's going to be totally clear to us that whatever we were looking for, it can't be found. There's really no other information to provide other than, given the data set that you provided and the filtration method that you provided, no results were to be found. But the option value isn't so good in cases where several different things might go wrong, because a null value would then just obscure those different possibilities. So this is a very contrived example of where an option value would be bad. We have a function that returns an optional value of a natural number. And we can see inside the body of the function that we have two different conditionals, two different blocks that could result in a null value. We'll just call them conditional 1 and conditional 2, or bar and baz. And then in the success case, we're just returning some natural number value. When we call this function, if we get null, then we don't know if it was bar or if it was baz. And so we don't have a way to diagnose the issue any further. We're effectively stonewalled in our debugging effort until we can gain more information through instrumenting the code or some other method. So those are the limitations of option. Next up, we'll take a look at the remaining two options for error handling, which would be errors and results. So the good news with both of these is that they provide us a way to give more context on a given failure. The Motoko official docs encourage people to prefer the result type. And quoting the docs, exceptions should only be used to signal unexpected error states. So when you're sitting down and designing your program, writing your program, it's a good idea to either at the outset or while you're building the program up, start to categorize all of the different errors that could occur. Call this and you can return a message to that effect saying that this is specifically what went wrong. So an exception should only happen when something very unexpected occurs. So a perk with the result type. So result is a module in the Motoko base library that relies on the variant type. Is that as with option values, the Motoko programming language, as well as other programming languages like Rust, will force you to unpack all possible values of the result type. And the result module basically allows us to provide two different variants in response. We can say this method was successful and here's the outcome, or this method was not successful and here is why. So let's take a look at this example, which details how we can use result type. So we have this canister which maintains a list of people, just maintains a list of their names. And we are defining at the outset, at the top of the file here, we have two errors which our program expects and will be able to handle. Then we have one function which just allows people to rename somebody in the list of people that this contract maintains. So it'll accept the name of the person whose name we want to change, and then what the new value for that name should be. And we are saying that in the result of a success. So when we're typing the result, the first type parameter will be the success type, and the second will be the error type. If successful, we're just going to return an empty tuple. And then if there's a failure, it's going to be one of our predefined failures here. So let's look at the first failure case here. We're going to say if caller isn't owner, we're returning a restricted error. So we only want the admin to be able to do this. And what we'll get out of this form of access control, if you will be a bit different from what we saw in the access control examples that we did earlier, where an assertion was just telling us, hey, it trapped on this line. This is going to tell us, hey, you're restricted. So hopefully that is more indicative, and a programmer could look at that and say, oh, this is restricted, or maybe a better name might be unauthorized. And then, you would sort of know what to do next as a programmer. You'd say, oh, like maybe I'm using my wrong principal, or perhaps, I transferred ownership of this to somebody else. It gives you some more recourse if you know what's going on. The second error case that we're looking at is not found. So basically, we're going to look through the list of names, and if we can't find the person that the caller wants to rename, then we're going to return a not found error. So, and then ... we would do whatever we were going to do, and then we would return the empty tuple value. And so if we were going to try these out, we could try calling these two different, try calling the same method called twice using different principles using a name which doesn't actually exist on the contract. We would see with the main identity, which would be authenticated because it was the one which created the contract, we would get a not found variant. So we went and looked for Randall, but he wasn't in the list, and so it's not found. And then if we wanted to call it with the alternate identity, well, we're not the admin, and so we get restricted. So the hope of what I hope what people can take away from this is that getting something back from a program like this, where it says, hey, there was an error, and the error was, this wasn't found, or the error was this, you're restricted, is more useful to you as a programmer than just getting my contract trapped for no reason, or for some reason that I can't tell you. So that's all we're going to cover for error handling for now. The short version of what we should take away from this is stick to result as much as possible for handling our errors, and generally steer clear of the error module for now. We're not even going to take too much of a close look at, actually, sorry, we're not going to look at the error module really at all in this lecture. If you're curious about it, it is linked up in the official documentation, which is linked in chat. So stick to the result type, and as you're writing your program, do your best to figure out ahead of time what the expected error cases would be, and then ensure that you're returning the correct results, the correct error in the right cases, and try to be as descriptive as possible. Think about what it would be like to try to debug your program without the context of having been the program's creator. And the third and final component for today's lecture is going to be dealing with cycles. So cycles is the unit, the economic unit that we pay for receiving computation on the internet computer. All of our canisters have a cycle balance, and in order to perform computation, we must be able to burn cycles. If our canisters fall below a certain threshold, our canisters will freeze. But we can also use cycles for a bit more than that. The Motoko programming language has a module called experimental cycles. So you import it the same way that you would import any other base library module, such as an array or buffer, etc. I think that the reason that it's called experimental cycles is that they're looking at moving it into a different place within the language. It might become a first class keyword at some point in the future. They're going to change the API for cycles in the Motoko programming language, potentially at some point in the future. So to get hands-on a little bit with what we can do with cycles, we'll create a little paid API. So looking at the access control example that we did earlier, where we have just a single method that returns a text result that we assume to contain a secret lasagna recipe, we are going to build an API that allows you to pay cycles to get that recipe out. So I'm going to jump over to VS Code here, and we'll just read through these two different canisters that we're going to use in this example. The first canister is going to be what you might want to call the API canister, and the second one is going to be what you might want to call the consumer canister. So over in the API canister, the one that's owned by our fictional grandma who has this lasagna recipe, we are going to capture the owner. We're going to define a price, and 1 trillion cycles is equal to 1 XDR, which is a small basket of currencies, and a million cycles is going to ultimately be like fractions of a penny. So grandma's given this recipe away. We're we're going to expose one method on this canister. We're going to call it recipe, and it's going to return a result. In the success, it'll be a text, and in the error, it will also be a text type. So we are importing experimental cycles from the Motoko base library. And the first thing that we're going to do is call cycles.available. And that's going to tell us how on the message that has been sent to this canister from the caller, how many cycles have been attached and how many cycles are therefore available for us to consume. I am going to just provide a link to the documentation for those in chat for the experimental cycles library, in case anybody wants to cruise over the API that it exposes there. We're going to be using all these methods in our demo here, or most of these methods here. We've got balance, which will return the actor's current balance. So the canister that calls this method, whichever canister that is, we're going to see the balance on the cycles ledger of that canister. As I was describing, available is going to tell us how many cycles are available on the message that is being sent to the canister. Accept is going to allow us to transfer some of the funds, however much of the funds we define in amount, from the available balance into our own canister's balance. So we're going to take those cycles from the caller and transfer them to ourselves. Then we have the add function, which will allow us to, before we send a message to another actor, add a certain number of cycles onto the message. And then we have finally refunded, which will tell us after we've added some cycles, sent a message off to another canister, they've accepted some of our cycles. Any cycles which weren't consumed on that call, we can call cycles.refunded, and they'll tell us how many we got back. So in Grandma's canister here, our API canister, we're gonna ask for how many cycles are available, and then we're going to check and see if the caller is the owner. If the caller is not the owner, we're going to do some additional logic. If they are the owner, we can just jump ahead and give them the recipe, because we don't need to make Grandma pay for her own recipe. If they're not the owner, what we're going to do is check and see if cycles that have been sent to us is less than the price. So somebody has called to ask for the recipe, but they haven't paid enough money, and we're just going to return an error. And the error message is just going to read, hey, you need to, pay full price for this, or whatever we want to say. And if they otherwise have provided enough cycles, then we are going to accept the number of cycles, a number of cycles equal to the price that we have defined, and then we will allow them to receive that recipe. And that's it for the API canister. So the other actor in this little example is going to be the consumer, somebody who wants access to this recipe. So we're going to define this get recipe method here. And for the purposes of our example, we're just going to say whether or not we want to pay, which is if we do say we want to pay, then we're going to add the cycles. And if we say we don't want to pay, then we're not going to add any cycles whatsoever. We're also going to use the Motoko base library's debug module, which, if you're not familiar, will allow you to see some debug messages printed out when you're using your local replica. It will not provide any additional debugging if you're working in any other network, if you're working on mainnet, most notably. unless, yeah, it's good for local debugging, but you'll want something else if you're trying to add debug messaging for mainnet. And we're going to just echo out our current cycle balance for the canister because we want to know that. That's interesting. And then we're going to define the actor for the API canister that we're going to interact with. So depending on where you're at in your Motoko journey, this line might look a little bit gnarly, or it might look totally natural to you. But what we're doing here is defining an actor. So we are typing it first with this component of the expression here to say this is an actor, and this actor has a method called recipe, which does not take any parameters, and then will return an asynchronous results with text for both failure and success outcomes. And then we are going to initialize a new actor using the principle of grandma's canister. This is pointing to some configuration that we've actually provided to our own canister, a parameter for our own canister. So by adding parameters to our actor class here, we are going to require parameters to be passed at time of deployment in order for this canister to be deployed. So whenever we deploy the canister, we're going to say you have to specify what the principal is for grandma's canister, so we know who to go and talk to when we want to get the recipe here. So we get the grandma actor set up, and then if we've said that we want to pay, then we're going to add the relevant cycles. And we want to be generous grandchildren, so we're going to send an additional 100 cycles along, even though we know the price is 1 million. And then we can go ahead and ask the API canister for the recipe. We'll perform that call. We'll await that. And then we will do another debug to say how many cycles we have been refunded. And then ultimately, we're going to return the recipe that we got from grandma's canister. So I think I'll jump over to command line here and just see if we can't run this this demo locally. So let's see. Let's do dfx identity main. Okay, let's create it. So I think I already have dfx running here, so I'm just going to shut it down and start it up again really quickly. Okay, and now we are going to deploy everything. I'm still on an older version of dfx, so I need to pass no wallet. And this is going to deploy a whole number of example canisters from all of the other portions of the lecture, but we're only interested in these two here, the experimental cycles A and B canisters. So it looks like those were installing well up until we ran into this problem here with the experimental cycles A is expecting an argument, as we talked about. So let me just see, I think in my slides, we have a dfx snippet that we can use for this. All right, so first we're going to deploy the first canister. So this is grandma's canister here. And then what we need to do is just determine what the principal of that API canister is, and we'll store that in a shell variable. So we now have, if we echo this out, this is the canister ID for Grandma's canister on our local net. And now we can deploy the consumer canister using the argument flag to pass in a list of arguments to the canister at time of initialization. And we're just going to pass in the principal that we've captured. So that has now deployed properly, which is great. And now, as main identity, I believe. So if we were to do dfx canister call experimental cycles A, we're just going to ask for the recipe. We should expect to get this back because we are the owner of this canister. However, if I switch to alternate identity, I can no longer access it. So what we'll do is we'll now go through the consumer canister and we'll say, I think it was get recipe. And this will require one parameter just to say whether or not we want to pay. So we're going to say initially, no, we don't want to pay, and we'll see what we get back from that. Okay, so the first two things we get back are from the debug library. We get our current balance of cycles. So we have a whole bunch of them. Our local replica assigns us lots and lots of cycles to play with by default. The second debug output is going to be from the cycles.refunded call. And we didn't add any cycles. We should not expect to receive any in refund, so that's perfect. And because we didn't pay, we did not get the recipe from Grandma. So why don't we just go ahead and change that to true. We do want to pay. And now we can see we have the same balance as before. We sent 1,100,000 cycles. The price was only 1 million, as we discussed. So when we added the cycles here, me too, Ted. We added an excess of 100. Then when we accepted the cycles over here, we accepted the price of 1 million, and so 100 were left over. Those are returned back to the caller, and now we can see that we have gotten Grandma's recipe back, as we would expect. We'll go ahead and call this one more time, just to see that our cycles balance has reduced by 1 million from our previous call. So those cycles have been consumed, or they have not been consumed, they have been transferred from the caller's cycle balance into the receiver's cycle balance. So that's a fun little pattern that you can use for anything that you'd like to. People have referred to a certain pattern of monetization. They've referred to a pattern called cycles mining. So if you were to provide an API that provides some functionality or some data, some utility that people value, then you could charge a certain number of cycles for each request and passively garner a bunch of cycles for your work. And that is almost it. So a more real world example of where you'll end up using cycles in production is for your NFT projects. I haven't spoken about CAP at length yet, but your NFT project doesn't get transaction history for free just because it's on the internet computer. And so a project like CAP helps to provide transaction history. But the way that it works, the CAP works, is it has one central canister which any NFT canister can go and say to that central canister, hey, I would like you to keep track of my transaction history for me, please. And that central canister, the router, will spawn a new canister that is dedicated to keeping track of transaction history for your NFT project. So it has to boil that down. If you want transaction history with Cap, your canister talks to Cap, and Cap spawns a new canister for you. Now, creating a canister costs cycles, and in order to send those cycles, you'll end up using the experimental cycles library, just like we did in the example today. And that is it. I think I was supposed to have a Q&A tile to be totally compliant with the Motoko Bootcamp rules and regulations. So we'll just add a Q&A heading on top of that. Yeah, that's it for the lecture. So any questions, please fire away.
Yeah, there's one person that let me allow them to talk.
Hey.
Hey.
Ellie, go ahead, please.
Yeah, thank you very much for your lecture. I don't know, I think I misclicked because I didn't want to say I don't have a question, but if I'm here, maybe I have to say something. So yeah, thank you, and I'm really looking forward to the for your NFT collection for the tarot NFTs and what's going next with it.
Well, thank you so much, Ellie. Thank you for making something of it. And looking forward to you becoming a full-blown Motoko developer who can contribute to that project and collect some bounties for it.
Yeah, for this I don't know, but yeah, maybe.
Okay, we have go ahead, Jorgen.
Hey, so I was wondering because Bob with Tonic Labs was mentioning that they were trying to come up with a solution for managing cycles on Entrepot, and what they came up with was really expensive. They needed something new. So what do you say is the best way to manage cycles for your canister?
Yeah, it's a great question. Entrepot has maybe a different scale of a problem than a smaller NFT project would have, where what you can see with some more sophisticated projects is you would set up a system that periodically monitors your cycle balance across your whole fleet of canisters that you're running. And to do that, you would need to develop an API that sits on each of those canisters, because by default, you can't just go to any canister and say, hey, tell me what your cycles balance is. So you need to expose that functionality. And then what you would need to do is just set up a war chest of cycles. And anytime you pull one of your canisters and the balance is too low, you would need to then just send them some more cycles. And so you would have to kind of design all of that system yourself. There isn't an out-of-the-box solution for that, but a number of projects have done it successfully. I've oversimplified it a bit, but there's that. And then there's, for a smaller NFT project, you're going to end up with a pretty low number of canisters. I have 3 or 4 different NFT canisters that I operate. And I top up cycles just by going to my Stoic wallet and sending some cycles over every once in a while. And I send over a lot, so I don't really ever have to do it. And I have a couple of methods that I'll just call manually to see what the balance is. I would recommend trying out, I think it's called, Canister Geek, from the User Geek team, which will give you a really nice dashboard for showing your cycles balance, as well as a bunch of other really useful metrics for your canisters. It's really easy to set up, and that'll give you an easy way to monitor your cycles in a little bit of an easier way than querying it in the command line each time.
Okay, cool, thanks. If you don't mind me asking, how for your typical NFT project of the 4 you've done, how high do cycle costs run?
That's a good question. I would say there's a couple of ways to cut that question. Generally, it's really low to start. Like it's you're going to spend, if you're hosting your assets on internet computer, I would say expect to spend in the ballpark of depending on the size of the assets, the number of assets that you're uploading. I've spent around $1 trillion to provision the assets onto the canister, and that's just for the initial upload, right? Like it's expensive to write to the blockchain, it's much cheaper to query, and then the number of cycles that would be used for querying those assets would then be pretty negligible. I have seen, though, a couple of other NFT projects that I think became the targets of some people who just really wanted to train cycles. And if you don't defend your canister from that type of attack, you can see your cycles get trained a little bit quicker, or maybe they're just really busy. But I've seen, a canister burn through maybe 13 trillion cycles in the course of a couple months, say. And 1 trillion cycles is I think it's about $3 and change. So not too much, depending on where you're coming at things from. Pretty affordable on the whole, but definitely something that you want to keep an eye on.
All right, thanks.
Yeah, thanks for the questions, Jared.
Anybody else? Well, it seems that we don't have any more questions. Well,
Okay.
no more questions. Thank you very much, Jorgen, for that brilliant presentation. Really appreciate your help. See you guys. I think we have one more tomorrow. Well, we have another lecture tomorrow. So see you guys tomorrow for the first lecture of the day.
Right on. Thanks for hanging out, guys. We'll see you at the lecture sections or the mentor sessions if you have any more questions. Thanks for showing up.